Hello, my name is Lucas Christowski, and I'll be speaking to you about some of the work we've been doing in the SiEPICfab consortium, with a focus on the efforts of a team of researchers at the University of British Columbia in Canada. First, I'll introduce the SiEPIC Research Training Program, which has been a silicon photonics training program running since 2007. Then I'll discuss the extension of the SiEPIC program, namely adding a fabrication component called SiEPICfab, Canada's Silicon Photonics Rapid Prototyping Foundry. I will discuss the electron beam lithography fabrication processes, associated process design kits, and component libraries. Then I'll discuss some details regarding lithography effects in our process and how we can compensate for them. Then photonic wire bonding as a means of packaging for silicon photonics and integrating silicon photonics with semiconductor lasers. Then I'll discuss how these fabrication processes are important for future work in optical and quantum computing. The main motivation for silicon photonics is to take advantage of mature fabrication processes which have been developed for the electronics industry. Billions of dollars have been spent leading to mature materials, fabrication processes, and design technologies. This offers the potential for building integrated systems containing numerous photonic components on a chip with a pathway for integration with electronics, either via monolithic or multi-chip integration approaches. As a user of these advanced silicon photonic manufacturing processes, I know the challenges we face are twofold. First, long turnaround times, and second, the fabrication processes are fixed. Sometimes it is useful to have access to rapid prototyping to test our ideas before we send the design to a manufacturing facility, and this is where SiEPICfab comes in. Let me tell you about our efforts in teaching people how to design silicon photonic chips. We first began silicon photonic training activities in passive fabrication processes, specifically using manufacturing at IMEC in Belgium. In 2012, we received government funding for the Silicon Electronic Photonic Integrated Circuits, or SiEPIC, CREATE program. We then started offering additional training workshops and courses, including active silicon photonic processes to train people in modulators and detectors, and this was offered by AMF in Singapore. We launched an online introductory course in silicon photonics in 2015, and it has been offered now about 15 times and uses electron beam lithography for rapid prototyping. In all our training activities, we emphasize the design cycle, where students start with a design and finish with experimental data that is compared to the model. Our workshops are typically 1 to 2 weeks long, where we go through the theory, modeling, design, layout, and help students develop a project proposal. Students then have time to create their designs in the form of a mask layout that is submitted to the foundry for manufacturing. Then there is some waiting time. Students either receive a chip, or in the case of the online course, we perform the measurements for all the designs. The final step is comparing the measured data with simulations and extracting relevant device performance and fabrication process parameters from experiments. The whole process takes about 1 year in the case of deep UV foundries, whereas we can complete the design cycle in 2 months using electron beam lithography. As a summary, we have offered over 20 in-person workshops, 2 of which have been offered online since the pandemic, and that was the passives and the actives workshops, which are described on our webpage. There's been a lot of excellent successes in terms of publications and new products being developed and new startups created. Our next online course starts on May 5th and is based on the fabrication processes that I will describe next. So I would like to describe the SiEPIC fabrication effort, or SiEPICfab. SiEPICfab is a consortium of companies and universities funded through industry contributions and matching government grants. We have come together to accelerate the silicon photonics development cycle, to develop new processes, and to use these technologies for new applications. The overarching goal of SiEPICfab is to provide silicon photonic research fabrication capabilities within Canada. The consortium members span the entire life cycle of silicon photonics chip research, design, fabrication, testing, and commercialization. One of our members, Applied Nanotools, commercially offers silicon photonics fabrication. And our members include design tool providers, automated test solution providers. Most of our work is centered around silicon wafers, and examples of fabricated devices are shown on the left. So how does SiEPICfab fit into the world of international silicon photonic foundries? First, there are many foundries, and they're all very keen to fabricate chips for us. Some foundries focus on high-volume customers, such as data center transceivers. Then there are low-volume research foundries such as IMEC, AMF, AIM Photonics, and others. Similar to the CMOS electronics world, some foundries are accessed directly, whereas others are accessed via multi-project wafer aggregation services, such as those provided by CMC Microsystems in Canada. Finally, there are smaller efforts which use electron beam lithography for fabrication, including at the University of Washington and Applied Nanotools and our SiEPICfab consortium. Our goals are to help research progress from early ideas, where rapid prototyping is really critical, towards commercialization. The approach we encourage is to first fabricate the devices and circuits using electron beam lithography, test the designs to make sure they work, then migrate the design to a low or high volume foundry. Along the way, we have lithography models available to help you predict the shapes of the fabricated devices so that you get much closer to your target the first time. This is first time right design, and it's particularly useful for devices such as Bragg grading filters, where smoothing from the lithography has a significant effect on the performance. This slide presents an overview of the differences between electron beam lithography, or EBL, versus deep UV lithography. The first difference is regarding the lithography. In EBL, the patterns are written directly on the wafer, whereas in deep UV, the patterns need to be written on a mask, and this adds time and cost. The other differences are not fundamental based on the lithography, but rather different philosophies adapted by the two approaches. The EBL processes are less mature, but they allow exploration of different materials and custom steps, whereas the deep UV processes are generally more mature and stable, and thus they're actually better suited for building large, reliable, and complex systems. Deep UV foundries typically offer numerous mask layers and numerous fabrication steps, and this requires excellent process control and process maturity. So combining the elimination of masks and fewer fabrication steps, the EBL approach leads to faster turnaround times, and generally an EBL process may return fewer chips and also costs less than the MPW foundry runs. Let me describe a little bit about the infrastructure at UBC that is available for SiEPICfab. The starting point for our process is electron beam lithography, and a new EBL system was installed 3 years ago, and it can handle small samples up to 200 millimeter wafers. It has an acceleration voltage of 100 kilo electron volts with a maximum scanning speed of 125 megahertz, and there are two writing modes, a high resolution and a high speed mode. And we typically use the high speed mode, and it achieves a 10 nanometer overlay accuracy between multiple writing layers. We have a new clean room that opened 1 year ago during the pandemic, and we've actually commissioned several new tools, including a dedicated etcher and a photonic wire bond, which I will discuss in this presentation. Our goals for the first 2 years of our operation were to develop basic passive processes for both communication bands as well as mid-IR in both silicon and silicon nitride, and to provide ways of getting light in and out of the chip through things like grading couplers and building phase shifters using heaters, and making sure that we have scheduled fabrication runs. So fabrication runs are publicly available via Applied Nanotools, and they use the electron beam lithography tool that I just described. And we've also recently demonstrated silicon detectors. On our roadmap, we're developing or planning to develop a few key technologies. First, we're looking at different ways of making detectors, including single photon detectors. We have efforts to fabricate different types of modulators. We're integrating 3.5 indium phosphide semiconductor chips for optical amplification and lasers, and this is using photonic wire bonds. Also connecting to optical fibers with photonic wire bonds. We have efforts in electronics integration. Typically we use wire bonding, and we also have some activities on integrating with advanced materials. So overall, our goal is to host a complete ecosystem from design, simulation, fabrication, test, and packaging. Let's discuss process design kits, or PDKs. So PDKs contain all the information that a designer needs to be able to successfully submit a design to a foundry for manufacturing. This includes a library of building blocks, example layouts, a layer table, and design rules. SiEPICfab primarily uses two processes for the work presented, and each which have an associated PDK. The first, and the most mature, is the Applied Nanotools HSQ process, and the second is an experimental SiEPICfab ZEP process. Both use the same EBL machine for rapid prototyping, and the main difference is the resist that is used for the exposure and patterning. So HSQ is a negative tone resist, and ZEP is a positive tone. And the PDKs are available online, publicly on GitHub. So let's talk about the strengths of the two resist types. Let's compare HSQ and ZEP. So the most important is the polarity. ZEP is a positive tone, while HSQ is negative tone. And this distinction is critical when choosing the process for fabricating a given design. In the HSQ process, what is drawn on the computer is written by the beam, and the resist protects the written area from etching. So it is natural to draw things like waveguides in this process. The ZEP process is the opposite, where what is drawn is etched, and hence it only requires a fraction of the writing area when you're creating small holes or gaps in the silicon. And so it's a natural choice for hole-based designs such as photonic crystals. So let's continue this comparison. HSQ is efficient when writing waveguides, whereas ZEP is less efficient for waveguides because you have to define the trenches on the outside of the waveguides, and so it requires a larger writing area. Now, on the other hand, if you're doing photonic crystals that use holes, then ZEP will be more efficient. So in theory, you could just do a reversal of your pattern from one resist to another. However, in practice, it doesn't work as well as we might hope. In both cases, the processes function better for low areas of exposure, and there's several different reasons from that. So in HSQ, what we find is that the designs that are well suited for it have a pattern density between 0 and a few percent, such as waveguides. And as the density of the patterns increases, proximity effects make it challenging to fabricate these devices. And in particular, we ran into challenges with devices such as photonic crystals. In ZEP, it's the opposite, where it's difficult to write narrow lines, and because you're writing a very high area that surrounds those lines, namely the trenches. So the processes use different resists. HSQ is thinner, and so it allows for small freestanding structures, such as the sub-wavelength grading devices, and I'll show an example. And it uses chlorine and or bromine chemistry. ZEP is thicker and is etched using fluorine-based chemistry. The thicker resist also makes it difficult to fabricate narrow structures, and they are prone to falling over. I should also point out that you can mix the two processes together. So for example, Applied Nanotools actually does both ZEP and HSQ depending on the types of patterns that are being written. So the differences in the processes, specifically the polarity and the resists, have led us to pursue two opposite approaches for making grading couplers. So first, I should point out that we could fabricate conventional partial etched grading couplers in both processes, and Applied Nanotools does offer that. But we're interested in rapid prototyping, so we desire a single etch process, and we use sub-wavelength engineering to create these grading couplers. So in the HSQ process on the left, we obtain repeatable fabrication by drawing continuous lines, which are sub-wavelength and about 100 nanometers in width. In the ZEP processes, these lines tend to fall over, so instead we design the grating coupler using holes that look like photonic crystals. So the photonic crystal is actually operated in the sub-wavelength regime, and thus it acts as an effective index material with a lower index value. There are two periods in the grating. There's the photonic crystal, and then there's the grating period, which is what diffracts the light out of the grating coupler. The grating consists then of two regions. One is the low effective index, which is the photonic crystal material, and the high index region, which is the bulk silicon material without the holes. Photonic crystals have many applications, including narrow line with filters, slow light, four-wave mixing, and the one we're particularly interested in is strong coupling to atoms for quantum information processing. So with the ZEP process, we have achieved quality factors up to about 130,000 in the near IR and 15,000 in the mid IR at around 2.9 micron wavelength. So next is contradirectional coupler filters. We have fabricated many times with the HSQ process these optical add-drop filters based on contradirectional couplers, or CDCs. The CDC is a two-waveguide, four-port Bragg grating structure, and it operates as a wavelength selective filter. We can configure the bandwidth to be approximately between 1 nanometer and 60 nanometers. We can adjust the central wavelength, and we can obtain excellent filter extinction ratio. In this example, which is fabricated by Applied Nanotools, the filter has a 50 dB extinction ratio. We have proposed using these CDC filters as high extinction ratio pump reject filters for single photon pair sources in silicon. The idea is to use spontaneous four-wave mixing in a ring resonator to generate the two photons, then filter the pump laser using an on-chip filter. Here we show that cascading three of these uniform grating CDC filters using their through ports can achieve a large extinction ratio of 60 dB or so. The plot on the right shows measurements of the photon pairs generated. It is a coincidence histogram, and this histogram was obtained by using time-correlated single photon counting to capture the photon pair events. And so this approach looks promising for on-chip generation of photon pairs. Let's discuss a little bit about electron beam lithography. So there are many parameters that need to be adjusted and optimized. The most important two are the beam current and the shot pitch. We have been studying different parameter choices with the goal of fabricating features down to 40 nanometers. The beam current is important because it affects the throughput of the tool, but on the other hand, we need to keep it low enough to keep high resolution patterning. We found that beam currents of 2 nanoamps results in 40 nanometer features. At that current, it takes approximately 40 minutes of writing for every 1 square millimeter of written area. And so our chips have a typical pattern density of about 1% over the entire chip, and so this amounts to a 1 square centimeter chip that is written in about 1 hour. So an effect that we've been studying is the impact of the local density on the performance of components. We have seen shifts in the response of devices depending on whether they are closely assembled in the layout, such as spiral waveguide gratings, versus devices that are loosely drawn on the layout. And so there's been several studies on optical lithography processes having an etch loading effect, where the feature size that's fabricated depends on the local pattern density. And so we're seeing similar effects here in EBL processing. We've been experimenting by placing tiling patterns around devices such as grating couplers and resonators, and we vary the tiling density around the device, in this example ranging from 0 to 10%. And in the ZEP process, we found that the radius of the holes decreased by 0.46 nanometers for every 1% change in the surrounding tiling density. So we believe there's two possible causes. First, the etch loading, and then second, it could be electron proximity effects. So we're developing a method for correcting this, and the idea is we can apply this on every component. The devices are parameterized in the layout, and so we can bias each device based on the local density effects. So here, what we've done is the hole radius was increased by 0.4 nanometers for every percent of density surrounding, and this improved the density dependence of the hole radius by 84%. So for future work, we'll study the length scales associated with these pattern density effects. And once we know this distance dependence and the strength of the effect, we anticipate that we can correct layouts based on a density map. So next, let's talk about photonic wire bonding. So photonic wire bonding is a new packaging solution, and it can make low insertion loss free-form connections between different optical components. And so it can be used to make connections from silicon photonic chips to other silicon photonic chips, or fiber arrays, or laser sources, or optical amplifiers. Photonic wire bonding is really useful for packaging. So it's a fast 3D fabrication approach for making optical connections. It results in really low insertion loss on the order of less than 2 dB per bond. And it has a very high placement and optical alignment tolerance. So there's a machine vision system that finds the components and very accurately draws the waveguide to the alignment markers on the structures. It's compact, it's mechanically stable, and it allows you to prototype a single product, and potentially this tool could be used for making millions of units. It's also useful for testing activities in the lab, so we can assemble and prototype things in a day. We don't need complicated and challenging alignment, active alignment nanopositioners, and so this is a very simple assembly, and we can build multi-chip modules with this approach. So let's describe a little bit about how it works. So first, we assemble all the chips on a common substrate and glue things down and then load it into the machine. Then you drop some photoresist onto the areas where you want to write the photonic wire bonds. The tool has automated image recognition software that finds alignment markers and waveguides, and then it calculates the waveguide trajectory that minimizes the bend loss. Then there's a laser, a femtosecond laser that uses 2-photon absorption in the photoresist, and that polymerizes the photoresist and turns it into 3-dimensional structures. Then you wash away with a developer all the resist that hasn't been polymerized, and that leaves the photonic wire bond. And then the final step is to encapsulate the photonic wire bonds with a cladding material with a lower index of refraction. This photonic wire bond tool was purchased and commissioned in the summer of last year, 2020. And we have a team of companies and funding agencies that are exploring this tool. And there's a picture here of the tool and the team in the clean room. One of the activities is to couple optical fibers to silicon nitride chips in this example from SiEPICfab. So these are chips with V grooves. The fibers have been slotted in, glued, and photonic wire bonds have been written, and then you can see loopback structures. So you can see in these experiments the results are showing on the order of 2 dB loss per photonic wire bond interface. And this is automated, so you're writing an array of optical fibers all at the same time. We're working on laser integration. So this is a 1.3 micron laser, which we want to connect to silicon photonics. And so the first step here was to develop a optical fiber to laser interface. And so all the two modules were placed on a carrier, glued down, and then the photonic wire bonds were written to attach to the laser. So this requires a little bit of optimization. For every new laser type, you need to figure out what is the mode field diameter and the location of where the beam comes out, and also some anchor points to attach the polymer photonic wire bond material. So you can see over 6 experiments, the coupling efficiency increased, ranging between 0% and 66%. And the light output versus current curves show a nice smooth response. The optical spectra also looks excellent. So you can see that there's a very high side mode suppression ratio, which matches the specifications of the laser. So it doesn't look like there are any issues in terms of things like optical feedback causing problems with the laser performance. So the procedure for fine-tuning the laser, as I mentioned, is adjusting the height. And so you can see in this case here, a 200 nanometer vertical offset resulted in a pretty large change or increase in the coupling efficiency. So from 26 to 66%. The tool itself has a placement accuracy of on the order of 10 to 30 nanometers. So it's very accurate in terms of where it can put the polymer material. These waveguides have bend radii, which are greater than 100 microns, so you don't have radiation. And you also need to make sure that there's some anchor points to attach the polymer materials. So in terms of integrating lasers with silicon photonic chips, we are pursuing an approach where we create a recessed cavity in the silicon. And the idea is to then drop the laser using a pick-and-place tool, recess it into the cavity so that the facet coming out of the laser is roughly at the same height as the photonic wire bond. The other benefit is that by removing some of the substrate and the oxide, you're getting down into the handle, and so now you have a good thermal conductivity from the laser down. So the lasers that we have access to have a thickness of on the order of 100 microns, and so we're etching down on the order of 100 microns. So it should be good thermal conductivity and good coupling efficiency. There's 2 approaches. One is using wet etching. So wet etching gives you these angled sidewalls, and the nice thing about these angled sidewalls is you can also deposit metal, and so you can then have the ground plane on the silicon wafer connecting to the backside contact of the laser, and that electrical contact can go up to the surface on the silicon wafer. And then we can use electrical wire bonding for the top contact, and then photonic wire bonding, and then encapsulation. The alternative is to use something like a Bosch process to do a vertical etch and put some metal on the bottom of the cavity, and then use use an electrical wire bond for both the top and the bottom contact of the laser by wire bonding down into the cavity. So these are 2 ways of creating the holes that we're looking at, and in both cases using photonic wire bonds. So in terms of alignment accuracy, I haven't mentioned, but the requirement on the alignment accuracy is very minimal. So the experiments that we're doing are placing things with tweezers by hand. You need on the order of 30 microns precision for the photonic wire bond to result in low loss. And so that should be pretty easy to achieve with an automated pick-and-place tool as well. So next, let's talk about a few of the opportunities for what we could do next. So in terms of photonic wire bonding, SiEPICfab would like to deliver to its members chip fabrication. And that would include design rules for photonic wire bond packaging, but also photonic wire bond packaging itself of things like optical fibers and arrays and lasers and amplifiers and so on. Now, photonic wire bonds, I think, are going to have quite a lot of opportunities. So biosensors is one area that's really exciting. Integrating DFB lasers or SOAs with silicon photonic evanescent field sensors. So tunable lasers or DFB lasers would be appropriate. For quantum photonics, we have opportunities for integrating single photon sources, single photon detectors for creating multi-chip modules. These would have a requirement for cryogenic operation. So we've been doing some tests to look at how these photonic wire bonds behave at cold temperatures, and so far looks promising. We also have activities looking at mid-IR wavelengths, and in particular we're working on a 2.9 micron wavelength spin qubit system. There's another area which is large-scale photonic systems, so things like optical computing and LiDAR applications, and there optical amplifiers would be beneficial. So if we want to create a system with lasers and silicon photonics and amplifiers, then these multi-chip arrangements would benefit from photonic wire bonds. Lastly, the tool we have is a research edition of the tool, and so we're able to develop new interfaces and different types of chips, and so we can work with different foundries to develop recipes specific for that foundry and specific for the lasers and SOAs. So a few words about the application optical computing, just in terms of some of the components that are required in the manufacturing. So this is a schematic of a photonic neuron, and it essentially looks like a transceiver architecture where you have high-speed modulators, high-speed detectors, filters, wavelength division multiplexing. And so on the input side, we need to get the light into the chip. And so this is either through grating couplers, edge couplers, or photonic wire bonds, which we can fabricate those structures. Multiplexing, we have a variety of technologies. I mentioned contradirectional couplers, but we also use ring resonators quite a lot. For the modulators, I talked about, I mentioned that we're pursuing different modulators. So PN junctions are a standard approach that we're doing, but we're also looking at polymers and graphene modulators. And we also anticipate building systems by including off-chip components, so specifically including the optical amplifier in these feedback loops for these neuromorphic architectures, and DFB lasers to power them, and this would be integrated with photonic wire bonds. And then we also have detectors as well. So these are silicon-based detectors that use defects in the silicon and a photoconductive effect. So next, optical computing. The first flavor here is based on linear optical computing, and there's also continuous variable computing. So similar kind of ingredients are required to build these types of systems. We need photon pair sources, and so this is the approach we're pursuing is the ring resonators using contradirectional couplers as the pump reject filters. For linear quantum computing, we're going to need various types of switches and modulators, and so again, those technologies are described are applicable. But on the receiver end, you will need single photon counting devices, and ideally these would be on chip, so that you reduce the coupling losses going from the processor chip to the single photon detectors. And so in terms of on-chip single photon detectors, these are based on niobium superconducting materials that are deposited on top of the waveguides. And these could be resonant structures or non-resonant. In the case of the resonant structures, you get nearly 100% quantum efficiency. So another approach for photonic-based quantum computing is to use spin qubits. So this is an approach that has been first proposed by Steph Simmons at Simon Fraser University. And it involves using a selenium atom as a spin qubit and creating a photonic crystal around it to couple photon to the spin, and then that creates a hybrid particle. And you can perform entanglement operations by having distant located spins and injecting photon pairs into these cavities. So the ingredients from a fabrication perspective are similar to the other technologies I described. There's the additional challenge of getting the implantation for the selenium and also the single selenium atom in the photonic crystal. So there's some challenges. So we're initially focusing primarily on the photonic crystals. We have to make the photonic crystals tunable. They have to be tunable in order to match the dipole transition of the selenium atom. And the selenium atom is working at 2.9 microns, so we have to make 2.9 micron tunable cavities with a high quality factor. And so that's what the picture shows in the bottom middle. I've already talked about the single photon pair sources and the single photon detectors, and photonic wire bonds, I believe, will be helpful here in terms of getting light in and out of the system to characterize it in the cryostat. So this summarizes the activities of SiEPICfab. And if you're interested in getting in touch, we have a variety of means. So we have a LinkedIn group, we have a mailing list where we send out a few emails a year in terms of announcements on things like fabrication runs and various types of courses. So you can take a look at our webpage, SiEPIC.ca. And if you're interested in partnering or finding out more information, you can see our contact information on this slide here. We do have an online course coming up, which is an introduction to silicon photonics. So if you want to learn about things like Mach-Zehnder interferometers, you can join us in May. And thank you very much for your time.